Welcome. In the previous lecture, we discussed charge sheet approximation and justified its usage. In this lecture, we would be discussing the inversion charge and depletion charge, and we will try to quantify their values with respect to say gate voltage, surface potential, and here we will use charge sheet approximation. So, what is the value of total silicon charge? So, what do we mean by total silicon charge? Look from the top within this gate, what the silicon charge in a unit area. So, total silicon charge would involve both the depletion charge as well as inversion charge. It would also involve mobile charges in oxide, which are all non-idealities, which we are not going to consider in this discussion. So, we are considering the oxide to be ideal, there are no interface states between the oxide and silicon. So, it is only the inversion charge and the depletion charge that we are considering. So, total silicon charge is the sum of these two. Now, this gate oxide is a capacitance, is not? So, and VFB flat band voltage is a correction to the gate voltage. It takes into account the inherent potential drop or band bending. So, now Vg minus VFB is the effective gate to body potential drop, so to say, and you have surface potential here. So, it is as if you are having the voltages across the two terminals of a capacitance, and therefore, this is the total silicon charge. So, that is the total, that is the charge across that capacitance. So, now what is the inversion charge? Inversion charge is this total silicon charge minus depletion charge. How much is the depletion charge? So, depletion charge is, we had already estimated it as, in the previous discussion, we had estimated it as the substrate modulation factor or body modulation factor gamma B into Cox into chi s. So, what is gamma B into chi s has a, it would in some sense it would be a voltage, isn't it? It's a kind of an equivalent voltage and across the oxide. So, that gives the body charge, total depletion charge in the body, and so we subtract that from this total silicon charge that we have. So, from that you are subtracting this depletion charge. So, that would give me the inversion charge. Now, we have to be careful with this. One thing is that we have considered depletion approximation here. So, depletion approximation, so in that we are considering the depletion region to be abrupt, that is, here it is depletion region and here it is neutral silicon, and the depletion region, in depletion region all the ions are exposed, all the dopant ions are exposed, and you can consider the hole and electron charge to be almost 0, and that is why you can consider the doping density of the substrate to be equal to that of the charge density. Now, this is an approximation. So, we are considering depletion approximation. Okay. So, the depletion approximation is one of the things which makes this expression, this inversion charge expression somewhat inaccurate. The other thing that we must keep in mind is that we are using charge sheet approximation here. Where are we using charge sheet approximation? In this basic expression itself, we are using charge sheet, here we are using charge sheet approximation. How are we using? So, we are considering that this gamma B chi s, this into Cox, this gamma B Cox root chi s is depletion charge. What does that mean? So, it means that inversion charge is not contributing. So, here when you apply Gauss law, so you are seeing that inversion charge, if you derive this, you find that you are considering the entire depletion region to contribute only depletion charge to make up for surface potential. That is, this expression has an integral of over this Gauss cylinder. So, integral of electric field over this Gauss cylinder, isn't it, if you remember in our previous discussions, and then we relate surface potential to the depletion charge. So, what we mean to say is that there is no contribution of inversion charge to the surface potential. When would that happen? That would happen if the inversion charge is just a sheet of charge, and therefore it's, so when you integrate it, so it is just a sheet of charge, and when you integrate electric field over the entire depletion region from here till the interface, you have no contribution of inversion charge due to inversion charge, but it is only a contribution due to the depletion charge. That is how this we have derived this expression. So, we are using charge sheet approximation in this, because we are saying that the surface potential is entirely because of the depletion charge. That is what we are inherently saying here, that the surface potential is entirely because of the inversion charge, depletion charge, I am sorry, depletion charge, and because of the inversion charge, the electric field is increased only in the gate oxide, not in the in silicon. So, what does it mean? There is no spread of inversion charge here. So, when you integrate from 0 to this point into interface, in that integral the charge contributions are all because of depletion charge, and inversion charge is just concentrated at the interface at z is equal to a single value, I mean it is not over a range of z. So, therefore, in the integral you do not get any contribution due to inversion charge, it is only a contribution due to depletion charge. So, there is this charge sheet approximation that we have used, and we have justified charge sheet approximation in our previous lecture. Yeah. Here we observe that there is an interesting function which we should take care of. So, it is this. So, we can write Cox as we can write inversion charge as Cox into Vg minus Vtp. Now, what is this threshold function? So, what is threshold voltage? Now, the threshold voltage and this threshold function look similar. This threshold voltage and the threshold function, they look similar. So, what is this threshold function? So, for a given value of surface potential, what is the value of gate voltage which would result in an inversion charge being 0? Now, it is not really that inversion charge would be 0, but according to this expression the inversion charge would be 0. In reality, what happens when you actually keep on increasing, say, surface potential? How can you increase surface potential? In this, if you increase the drain voltage, surface potential near the drain will keep on increasing. So, that is one way of increasing the surface potential without changing gate voltage. So, when you are keeping on increasing surface potential, the depletion charge increases, gate voltage is the same, inversion charge would keep on reducing. As inversion charge keeps on reducing, the vertical electric field keeps on reducing, isn't vertical electric field from gate to the channel, it keeps on reducing, and therefore, the spread of inversion charge, now the spread of inversion charge, it's now the inversion charge is very small in value. So, the spread of inversion charge itself, you cannot say that it is now just a sheet, the electric field, vertical electric field itself is now quite small. So, you would find that this expression, which is based on charge sheet approximation, may not be very well valid when inversion charge is actually near 0. So, for Qi equal to 0, transverse electric field is small. So, you would say that Qi is tending to 0, not equal to 0. So, the transverse electric field is very small, spread of electrons greater. So, the transverse electric field or vertical electric field is small. So, spread of electrons would be greater because they are not pulled in the positive x direction. Now, so what you would say is that charge sheet approximation is now somewhat less valid. Charge sheet approximation needs some consideration. So, it may not be so well valid. So, therefore, at Qi equal to 0, it is not that this expression is exactly valid, but it is valid for larger values of or smaller values of surface potential. For a given gate voltage, if you keep on reducing the surface potential, then there is inversion charge as well as depletion charge. Inversion charge, if it is, and you are also increasing the vertical electric field. So, inversion charge, suppose it is concentrated all at the silicon dioxide interface in silicon. So, then this expression is quite well valid. So, when you keep on increasing the gate voltage or reducing surface potential, you observe that this expression is better valid. So, now let us come back to threshold function. So, threshold function is these three terms taken together. So, what does it mean? If you increase for a given gate voltage, if you keep on increasing the value of surface potential, then a certain value would come where this inversion charge according to this expression, not in reality, becomes 0. So, that we call the threshold function for that given surface potential. Okay. Now, let us make another observation. These two expressions, they look similar. So, now for flat band voltage, for the band bending being equal to 2 phi f, this is itself the VTO is the VTB. So, for values of surface potential which are smaller than 2 phi f, what is the inversion charge? So, that is what we are attempting from here. So, that is Vg minus Vtb. So, VTB is a function of surface potential. Mathematically, there would exist a value of Vg which is equal to Vtb, where the inversion charge would be 0. Okay. Now, let us look at this VTB. Does it give us an information regarding the inversion charge? Can it give? So, for a given chi s, for a given value of surface potential, we know the VTB. So, that corresponds to the gate voltage, which would mathematically give Qi equal to 0. Now, suppose you keep the surface potential the same and you increase the gate voltage, what would happen? Because the surface potential is the same, but the gate voltage has increased, the inversion charge would increase now from 0. So, does this, so this should give us an information about the inversion charge. So, that is what we will try to see. So, what is the value of, say, now where will we use this? We will discuss it later. So, this is 1 plus, so you get this from this expression. Now, let us call it N. Why are we calling it N? We will discuss that later. So, for a given gate voltage, so let us plot VTB versus surface potential. So, surface potential would be varying from source to drain in this case. So, for a given gate voltage you plot this. So, what do you observe? You observe that for larger values of chi s, though this is non-linear, it looks like almost line. That is because for larger values of surface potential, this factor becomes smaller. So, this is the non-linear factor. This has smaller importance, and therefore, n is constant. N is almost a constant. Otherwise, n is a slow changing function with. So, what is the inversion charge? Inversion charge, as we see, is this value, isn't it? This is the inversion charge. So, can we see that in this plot? So, in this plot, this gate voltage minus whatever is the voltage here, gate voltage minus whatever is the voltage here. So, gate voltage is this value minus this divided by Cox should give me the value of inversion charge. I mean, into Cox should give me. So, how do we represent that pictorially? In this figure, let us see. For a given value of Vg, now this is again equal to n. So, what does it mean? So, I have, suppose this is the value where Qa is 0. So, that is the point where Qa is 0. So, gate voltage, this is the gate voltage where Qa is 0. So, now you change the surface potential. So, you change the surface potential, then change in VTB can be obtained from a change in surface potential into this slope factor n we call slope factor, isn't it? So, therefore, you have this is the change in surface potential, this is the change in surface potential being shown, this from here till here is the change in surface potential from here till here, and in that into n gives me the change in VTB. Fine. That would also give me the change in the value of inversion charge, normalized inversion charge. That is inversion, it is a kind of voltage, inversion charge by C. It has units of voltage. So, now what is the inversion charge here at this point? At this point I have said the inversion charge is 0 and I am tracing this expression itself through this line, and at this point I am saying that the surface potential is different. I have the same gate voltage, this is the value of VTB, and this difference is also this inversion charge by Cox. That is what I am now saying. So, how is this going to help us? So, now you plot VTB versus chi s and find out the point where Qi is equal to 0 mathematically. Now, you change the surface potential, you can estimate the inversion charge. So, this is interesting. So, how do you estimate the inversion charge? Using simple expressions. So, this difference between the gate voltage and VTH, the gate voltage and VTB, that is Qi by Cox, the difference. So, how the inversion charge varies or increases. Now, let us estimate the value of the slope factor n. Let us find out the value of n for surface potential being 1.95. So, we are not saying 2.5. So, ideally it has not entered the strong inversion regime. So, what is the value of n here? What was the value of our gamma b? In the previous discussion we had obtained the value of gamma b. So, that is 1.7. So, gamma b was 1.7, that is what we had estimated it to be, 1.7 root V divided by farad per centimeter, that was the unit we had seen. So, fan yeah. So, now let us estimate the value of n for phi f, which is just the onset of some inversion charges are building up. It is not 2 phi f, it is just phi f. Okay. So, what is this? This is 2.2. So, we can see that there is a change in the value of n, and that is around 15% for these two extreme values. One is just the onset of say moderate inversion, the other one is just the end of moderate inversion. So, you are finding a little change in the value of n. Let us also see this in more detail. So, as chi s keeps on increasing, n becomes almost a constant, because the second term in this expression becomes less important as chi s becomes larger and larger as surface potential increases. So, therefore, for larger surface potential this is almost constant. Now, even for an extreme value of gamma b, which is 40 ut gamma b square, that is an extreme value of gamma b. Even there you are getting the value of n to be almost constant, and it is only for small values of chi s, small values of the surface potential, that this n is now not a constant. Okay. So, this we can keep in mind. So, whenever we are dealing with values of chi s which are within this range, you would find that n is fairly constant. Let us define pinch of voltage or pinch of surface potential as chi s equal to chi p. So, what is this chi p? This corresponds to this is the surface potential at which Qi is equal to 0 mathematically. So, what is that? So, if we look at our VTB, so it should be for chi s equal to chi p, Vg equal to VTB. It is then that inversion charge would be 0, is not it? So, let us look at our previous expression. Vg Qi equal to 0 is equal to Vg minus Vfb minus chi s minus gamma b Cox root chi s, is not it? So, what do we mean by this? Now, the value of chi s for which this happens, we are calling it chi p. So, therefore, we can rewrite this as, we are rewriting the same expression this way. So, now what is the value of? So, which of these plus and minus, which sign would hold? So, this square root of chi p, so that is a surface potential, cannot be negative. So, therefore, it is this positive sign which holds. So, we must leave this negative sign here. So, what is the value of chi p? Just square this VFB. So, all this is under the square root. So, let us differentiate both these braces. So, once this I have just simplified the square root of chi p, I have just squared both the sides. So, once you do this, you get an expression for chi p. Yeah. So, now chi p is a unique function of gate voltage. It's a unique function of gate voltage. So, why is it so? So, for this pinch of voltage, surface potential being pinch of voltage chi p, inversion charge is 0. So, since inversion charge is 0, the entire electric field everywhere within the depletion region, that is silicon, and in the oxide is entirely determined by the inversion depletion charge itself. And therefore, it is when you consider depletion charge and determine the electric field, integrate it over vertically, you get the gate voltage. Whereas, when there is inversion charge, so now suppose the surface potential is reduced below, so below the pinch of surface potential chi p, inversion charge would build up. That inversion charge for a given value of surface potential, that inversion charge would also contribute to the electric field in the oxide. Since we use charge sheet approximation, we would say that it would not contribute any value to the inversion any value to the potential drop in silicon, but or electric field in silicon, but it would contribute to the electric field's value in the oxide. So, therefore, gate voltage can be the same, but the surface potential can be smaller than chi p. So, for a smaller surface potential than chi p, the depletion charge is now reduced, but inversion charge can increase. So, therefore, what we are saying is that chi p is the largest value of surface potential that can be attained for a given gate voltage, and when you keep on increasing the surface potential for a given gate voltage, you are reducing the inversion charge. So, let us estimate the value of chi p for a given gate voltage. Let us do it for gate voltage equal to 1 volt. Flat band voltage we had earlier used in our lectures to be minus 0.7 volts. So, for these values, let us estimate the value of chi p. So, what is that? Vg minus Vfb, which is 1 volt minus 0.7 volts, plus gamma b square, which is 1.7 square into square root of Vg minus Vfb, which is 1 divided by gamma b square plus 1 by 4 minus half. So, what is this? This turns out to be 0.5 volt. So, this is so we have estimated the value of chi p for a given value of gate voltage or flat band voltage. Now, let us estimate the value of inversion charge. So, inversion charge, as we have been discussing, is total silicon charge minus depletion charge. So, what is the total silicon charge value? That the total silicon charge value we had already estimated it and it was in terms of the function f. In terms of function f we had estimated. So, we had said that it is proportional to f. And what is the value of gamma b? We had written it to be gamma b is and total silicon charge is in terms of function f, we write the total silicon charge to be epsilon silicon into f. So, in terms of gamma b, we can write total silicon charge to be, we can write it this way. So, and since this is an n channel device and we are operating in either in the moderate or weak inversion or in strong inversion regime, a negative sign comes here. Okay. So, using this, what would we say? We would say that the inversion charge is total silicon charge minus depletion charge. So, in strong inversion, what is the or in moderate inversion, what is the value of f? What is the expression for f? It is this. The accumulation term, there are 3 terms, depletion charge term, inversion charge term and accumulation term. The accumulation term vanishes. So, it turns out to be this in moderate inversion or weak inversion, because this is larger than 1. So, that 1 is neglected. So, you get this to be the expression for f approximately, and for depletion charge it is this. Okay. So, therefore, because we are using charge sheet approximation, and the depletion charge we are saying is just neglect the inversion charges, and you can neglect, and the surface potential is the same because it is entirely because of the depletion charge. So, depletion charge is this. So, you are having this as the inversion charge. Now, what is important here? So, when does the inversion charge become 0? Inversion charge becomes 0 when these two terms are equal. When would they be equal? This exponential term can be 0, it has to be 0 then. So, and when would this be 0? So, this exponential term, this exponential term would be 0 only when should be 0 if qi equal to 0, and this can happen only for chi s tending to minus infinity, otherwise it would not happen. So, that is where I was saying that this that our earlier discussion where inversion charge was 0 for pinch off surface potential chi p, that is an approximation, and it is so with our mathematical expression. In reality, the inversion charge would never be 0 for these kind of surface potential values. So, our expression, so inversion charge being 0 and all that, so is valid when these can be, so when is that valid? So, for larger values of surface potential, what happens? Now, this term also, so this first term becomes much larger than this. So, the first term should become much larger than this, only then the inversion charge attains a certain significant value. So, when does that happen? So, we can say that chi s, this numerator should be larger than ut at room temperature 26 millivolts. So, if this numerator is much larger, say 2 times or 3 times this 26 millivolts at room temperature, then we would say that inversion charge attains a somewhat significant value, and then our earlier expressions start making more sense. So, for very small values of surface potential, or to word it more correctly, for very small values of inversion charge, the earlier expressions that we had discussed were relating to threshold function, the inversion charge being related to threshold function and gate voltage. Those expressions are not very well valid for very small values of surface potential. So, today we have discussed the pinch off surface potential and threshold function, using which we are able to estimate the value of inversion charge, and also we have discussed the validity, when are these expressions somewhat more accurate and when they cannot be used.